So there's a number of topics that I would like to include within the modeling class, but we can only cover so much material. They're important to your modeling, but a little bit more of a parallel with modeling. So I'm going to wrap some of them up here, and there's more information on the website on some of these. So here we've got a data set from NOAA, a shapefile that I created this simple map in that shows temperature range within the United States. And take a look, we've got the same temperature range here in this data set for this entire area, or for, most of Western Oregon over here, or the entire Central Valley of California. And think about the complexity that exists within there that is not represented on this data set. So we need to think about that whenever we're dealing with data sets, especially categorical data sets, about what's really there as opposed to what we're seeing in the data. So where a lot of our data comes from is field data, like this data, which is a map of the US weather stations. And my lab at Colorado State, lab I was in, did some work in Escalante National Monument, which is down here, which has, I think it only has like one weather station actually inside of it, but 3 nearby. And from that, you can then get 1 to 4 kilometer data on the weather within Escalante. So the thing to think about is, where did that data come from? What does it really represent? And of course, you can see there's a lot of complexity in Escalante National Monument that we may miss. So most of that data comes from interpolated data, where we have a set of points that were measured. Even these have some level of uncertainty, and then we interpolate between those points with some method. Now, in order to do that, we do need to show that there is autocorrelation between those points, and we'll talk about that in a second. So same thing is true of old elevation dams. Now, this is less likely today because we tend to get them from LiDAR or from the radar telemetry missions from the space shuttle. And they still are points that are received back, but they're in a uniform grid for radar, and for LiDAR, they actually are points that would look like this at very high density. Again, interpolated. So whenever we interpolate, we're filling in gaps between the points without knowledge of what's really there. We can do this because of the first law of geography, and that's that everything is related to everything else, but near things are more related than distant things. So in other words, you could think about here in Humboldt County, we look around, we have big trees. We have big redwood trees. Our trees are either conifers or tan oak or madrones, certain species of trees. And if you move to the Central Valley, the trees are going to look very different than they do here because the environment's different. But also there's a spatial relationship. You're only going to find redwoods where there's other redwoods because they disperse over time. So everything is related to everything else, but near things are more related to distant. Now, this is a general concept, and it's not absolute, of course. But this is what autocorrelation is based on. In other words, things that are close together are correlated with each other. And so here we've got a picture of that where we have things clustered versus dispersed. Okay, these would be more correlated, okay, or have more autocorrelation. And there are measurements for this. There's a number of them. Moran's eye is one of the most commonly used, and basically it's an index measurement that -1 would be perfect dispersion. In other words, nothing is correlated with those things around it, and then 1 would be perfect correlation. Now, you can't actually get to 1 because, as you can see, you group things here, but then next door neighbors right here are a little different, and next door neighbors here are different. So you can't ever get to 1 in a data set that has even 2 values in it, 2 different values. Okay, but built into ArcMap as well as other GIS packages. Here's the equation where n is the number of points, and we have to go through and sum a set of weights for all points against all other points in the data set. Okay, so here's our measured value for I, measured value for J. We subtract those from the mean, so we're finding the difference from the mean, how different they are from the average, multiplying that times a set of weights, okay, and then summing those up for all points against all other points. So in other words, if we had 3 points, we'd take the first point against the second and third, then we'd take the second point against the first and the third point against the first and the second. So we have all combinations. And then we divide by the square of that difference, because we're squaring it here, and divide, and then sum those so that we bring it back down to go from 1 to -1. And then W is just a sum of all the weights as well, so we take care of this term. All right, so with Moran's I, here's an example where here you're going to have high autocorrelation, about as high as you can get, again with 2 different values, but notice it's 0.857, so we can't ever get to 1 in a real data set. You can get to -1 if everything is completely dispersed or in checkerboard pattern, so no autocorrelation. In other words, the neighbors are as different as they can be from each other, and then different levels of autocorrelation within there. Another way to look at this is if you just look at a linear data set, here's high correlation. In other words, 0 is very similar to 10, but it's not similar to 70 or 80 or 90. So as the distance increases between 2 points, their value is larger in difference as well. Each of these points has 10 values between it, but much larger differences as you move further. At random, 0.05, so close to 0. And then if you have the opposite, where 0, 1, 0, 1, 0, 1, in other words, this point is more like this one, something that's far away, than it is to a neighbor, then you have the opposite of autocorrelation. Now, this is very important because if we're going to do interpolation, we really need to know that there's autocorrelation in our data. Sometimes autocorrelation will mess up our models, but for interpolation, it's absolutely critical that it be there, because if this is the situation where our points that are near each other are more different, then we can't interpolate across this data set, because interpolation assumes that those in-between values are related. In other words, if we took something like this, and we had these measurements along a slope, and we want to interpolate between them, we have to know that there's a relationship between them, that it's not just random or the inverse of random, which would be no autocorrelation. So the way there's different methods for doing interpolation. One of the most common is inverse distance weighting. It's very simple. Basically, you take a point, and then those points, to compute this point, we look at the points around it, and we average them together, but we do it based on their distance from the point. In other words, this point would have more weight in computing the yellow point. This one would have less. This one would have even less because it's the furthest away, and then points outside the circle could just be completely ignored. And so to find this pixel, we're effectively averaging these but weighting them based on the distance. So that's the inverse distance. In other words, those that are far away are weighted less. So it's the inverse of distance. So to do this, you obtain points with measurements. It could be any different type of measurements. Maximum tree height, slope, weather data is typically interpolated. You then evaluate the data, look for autocorrelation, and then interpolate between the points. Usually we create a raster from a point set. So effectively you think of the raster as being a grid of points, and we're computing each one of those points using one of these methods. Inverse distance weighting is one of the most common. It's also very fast. It produces nice looking rasters, but they're not statistical. Kriging is the one we tend to use the most within a statistical, both because it is a statistically based interpolation method, and it actually produces a statistical surface. Splines make very nice looking rasters, and those are great for making maps. But again, they're not statistically based, and they don't produce an error surface. And then we can always convert the raster to vector using contours for visualization if desired. And that was probably how that initial NOAA data set was created. So let's talk about simple interpolation. So if we're looking at the raster data from the side, so think of this as being a spatial cross-section. Maybe this is a slope that we have survey points along, and we need to have a dim of the whole area. So I'm just looking across the area. Maybe this is a side of a hill, and then the measured values, elevation, go this way, but it could be anything. It could be temperature, precipitation, tree height, soil, phosphorus or organic content, all kinds of things. So linear interpolation would simply measure between these and draw effectively a straight line. Okay, so that's the pure term of linear interpolation. However, when we do this to create a raster, we're really creating pixels at discrete spots. So this works by finding the closest value, often integers, along a line that is going between these points. Okay, so we have a linear interpolation between these points, but we're really grabbing the closest value to the center of that pixel. Now, one of the things that's important here is notice that here we have a value of 35, here we have 36, here we have 50, we have 47, 55. When you do interpolation, typically the original points are not maintained. So when you convert it to a raster, those points disappear. We've lost that original data, and we now have something that has, error at that point that's been introduced, and then we interpolate between them, so there's actually more error in between. Here's an image of inverse distance weighting from a data set. Kriging, again, doesn't look as nice as inverse distance weighting. And I should mention these breaks in here are from setting a perimeter around it. It's when different points are included or not included. Kriging, yeah, doesn't look as good, but it's more statistically accurate and you can have an output surface with it that gives you the error estimates. And then splines, very nice, very smooth, look cool. More for visual and background than for analysis and modeling. Within ARC, we have IDW Kriging, natural neighbor. That's just picking the closest one to the point. Splines, and then you can do trends as well. But really, we've got more than enough tools in R to be able to do a better job doing trends. Also in ARC, the thing to really mention is this geostatistical wizard. It's a very powerful piece of software that allows us to do autocorrelation analysis as well as interpolation. So for using inverse distance weighting, excuse me, no values outside the available range of values. In other words, it assumes zero uncertainty. It's going to put the values as close to the pixels as possible, and it smooths out the data. It does that. Here's again the equation. You have your interpolated point, and then you have some distance, and it's going to go ahead and take the value for each point, divide it by the distance, sum those up, and then divide that by the sum of the inverse distances. Okay, and that will give us a new value at this point. Kriging is very different, and typically we run a SemiVariogram, which is an analysis of the autocorrelation. And that's one of the most important pieces, is to be able to look at the autocorrelation. Moran's eye will tell you how much autocorrelation is in it. SemiVariogram will give you more information. We'll talk about that more in a second. It'll also help you determine the parameters for Kriging. Kriging does an interpolation of raster. It assumes stochastic data. So unlike IDW, it assumes there is some error. It doesn't try to fit the surface through the points exactly. And again, it can provide an error surface, which is very cool. Okay, so SemiVariance. SemiVariance is the change based on distance. In other words, if we got 2 points, each one has a z value. So this could be elevation. It's an easy one to think of. 2 elevation values. And what we want to find is what's happening over space and time with this. So what we can do is we can first compute a variance between these two. Variance or change between these two, and that would be z sub I minus z sub j. That'd be this magnitude here. Okay, and then we square that. That becomes our variance. SemiVariance is then dividing that by 2. Don't know why they divide it by 2, but they divide it by 2. So SemiVariance is what you'll see for analyzing. Now, what we can do is then plot that by saying, well, here we've got 2 points, and let's say they're separated by 10 units. In other words, the distance between them is 10, but the change in magnitude, elevation, or whatever the value is 2. So that would put them here on this chart. So distance out is 10, go up to 2. Okay? Now, the reason that's important is because this is a semivariogram, and that's what it does. It takes all of our points, and it looks at the distance between the points and their semivariance, or the square of their difference divided by 2, and it plots it this way along this axis. So now we have a graph that shows us how things change based on distance. Oh, and I should have said, for each of these points, we've done, again, combining each point against itself. So we would take, again, if we had 3 points, take the first one against 2 and second and third, second one against the first and the third one against the first and second. And because of that, sometimes you have to downsample your data because this is computationally intensive to do this. But here's our graph of semivariance, or the change in value over distance. And then you can fit a curve to it. And this graph shows that there is autocorrelation. In other words, it's a graph of autocorrelation in that these points that are closer together also have more similar value or less variance than these points. Or as you move away, things change more. When you're close, they're similar. When you're farther away, they're more different. There's some definitions for using this. This is called the Nugget, where it intercepts with 0, so that's the y-intercept effectively. The sill is when it starts to flatten out, and then the range is the distance for when it starts to flatten out. And you'll see different autocorrelation curves. This is what we're looking for, is one that does something like this. If they're flat, that means there is no autocorrelation. If the points are all over the place, you will tend to get it flat, but you can also get some strange things, which usually means there's no autocorrelation, or you don't have enough points to demonstrate the effect. Couple of definitions around this. There's different types of relationships between things, and one of them can be directional. This is harder to deal with, and it can change your autocorrelation results. In other words, autocorrelation can be based on direction as well as distance. So isotropic would be that everything is the same in all directions, which is what usually we're looking for and usually what happens. Distribution of galaxies would be an example. Anisotropic, so the opposite, and tropic means direction, iso same, so anisotropic would be different directions. And that would be something like trees will blow down, and you can see that there is an effect going this way, but then there's a different effect going in a different direction. In fact, we would have autocorrelation going in this way because of this repeating pattern if this was a remote sensing image, but we wouldn't have autocorrelation in this way. The Geostatistical Wizard in ArcGIS allows you to have analyze autocorrelation and then interpolate based on direction as well as distance. It's pretty cool. Here's some different software, and of course R has a bunch of interpolation tools in it as well, and lots of resources out there on autocorrelation and interpolation. Thanks.